Close your eyes for a moment. And think about water. Not the ocean. Not a river. Not a storm moving across a distant mountain range. Something smaller. A single drop of water. The kind that forms on the outside of a cold glass on a warm morning. The kind that hangs from the tip of a leaf after rain, trembling, catching the light, before it falls. One drop. Colorless. Weightless, almost. So ordinary that we pass through thousands of them every single day without pausing to consider what they are. Now hold that drop in your mind. And consider this. The water in that drop is old. Not old in the way that a mountain is old, or a fossil is old, or even a star is old. Old in a way that has almost no parallel in the ordinary scale of human experience. The water molecules in that single drop have existed, in one form or another, cycling through ice and ocean and cloud and rain, for approximately 4.5 billion years. Since before this planet had continents. Since before it had oceans. Since before it had an atmosphere worth speaking of. Since before life existed anywhere on its surface. That drop of water is older than almost everything you have ever touched. And the question of where it came from, how it arrived on this planet, how it survived, why Earth has it and Mars does not, is one of the most extraordinary unsolved questions in all of science. Tonight, we are going to follow the water. Back to the beginning. Back before the oceans. Before the rain. Before the first living thing ever drew it through its body and used it to make something that had never existed before. Back to a time when this planet was molten rock and poison gas, and the water that now covers 71% of its surface had not yet arrived. So let the day go. Let the weight of it dissolve, the way salt dissolves in water, completely, without resistance, until there is no trace of it left. Breathe slowly. And let your mind travel back. 4.5 billion years. To the beginning of everything you have ever drunk. Chapter 1, The Young Solar System. To understand where Earth's water came from, we need to understand the world into which Earth was born. Not the world we know now. Not the world of blue oceans and green continents and white clouds drifting across a sky that has been breathable for hundreds of millions of years. The world of 4.5 billion years ago. A solar system still in the process of assembling itself. The sun had recently ignited, a young star, perhaps only a few million years old, pouring enormous quantities of radiation outward in all directions. Around it, the disk of gas and dust from which the planets would form was still present, a vast, flat structure of material slowly clumping together under gravity, colliding, merging, growing. This is the protoplanetary disk. And within it, the story of Earth's water begins. The disk was not uniform. Close to the sun, within what scientists call the frost line, or snow line, temperatures were too high for water to exist as ice. Any water molecules in this region existed only as vapor, too energized to condense, quickly swept outward by the solar wind or broken apart by radiation. The early Earth formed inside this frost line. In a region of the solar system where water, in any stable solid form, simply could not persist. This is the central mystery. If the region where Earth formed was too hot for water to survive, where did Earth's oceans come from? Chapter 2, A Planet of Fire. The early Earth was nothing like the planet we know. In the first 100 million years of its existence, it was a world of extraordinary violence. A world of continuous bombardment, the surface struck, again and again, by planetesimals, asteroids, and other rocky bodies left over from the formation of the solar system. The energy of these impacts was immense. So immense that the surface of the early Earth was likely largely molten, a global magma ocean, kilometers deep, glowing with heat, the rock itself liquid. Any water that might have arrived in this period would have been vaporized almost immediately. Steam, rising into a thick, poisonous atmosphere of carbon dioxide and nitrogen and hydrogen sulfide, mixing with volcanic gases from below. Not an ocean. Not yet. Not even close. And then, approximately 4.5 billion years ago, something extraordinary happened. An object roughly the size of Mars, moving at enormous speed, struck the early Earth in a collision so violent that it partially vaporized both bodies. The debris from this impact, rock and vapor and the remnants of 2 planets, spread into orbit around the Earth. And over the following months and years, that debris coalesced into the Moon. The giant impact hypothesis, the leading scientific model for the Moon's formation, has profound implications for the question of Earth's water. Because the impact that formed the Moon would have generated so much heat that any water present in the early Earth at that point would have been driven off completely. Vaporized. Lost to space. If this model is correct, and the evidence for it is substantial, then the Earth, in the aftermath of the Moon-forming impact, was essentially dry. A rocky, molten, waterless world. And yet, here we are. On a planet covered by oceans. The water had to come from somewhere. Chapter 3, The Delivery Problem. Scientists have a name for the challenge of explaining how Earth got its water. They call it the delivery problem. The question is not whether water existed in the early solar system. It clearly did, and does. Water ice is one of the most abundant compounds in the universe. It coats the surfaces of asteroids. It fills the hearts of comets. It covers the moons of Jupiter and Saturn in layers kilometers thick. The question is how that water got from the cold outer solar system, where it could exist as stable ice, to the inner solar system, where a rocky planet was assembling itself in a region far too warm for ice to survive. 2 main candidates have dominated the scientific debate for decades. Comets and asteroids. Comets are, in many ways, the obvious answer. They are composed largely of ice, water ice, carbon dioxide ice, and other frozen compounds mixed with dust and rocky material. They are spectacular when they enter the inner solar system. Their ice is vaporizing in the heat of the sun to produce the long, luminous tails that have captivated human observers for thousands of years. And in the early solar system, they arrived in enormous numbers. The period known as the Late Heavy Bombardment, occurring approximately 3.9 to 4 billion years ago, saw the inner solar system subjected to an intense period of impacts from comets and asteroids. The evidence for it is written in the cratered surfaces of the Moon and Mercury, preserved for billions of years in the airless silence of those worlds. If even a small fraction of the material delivered during this bombardment was water ice, the oceans of Earth could have been filled many times over. It seemed straightforward. Elegant, even. But then the measurements came back. And the answer was not what anyone expected. Chapter 4, The Isotope Problem. Water is not a single thing. Most water molecules are composed of 2 atoms of ordinary hydrogen and 1 atom of oxygen, the familiar H2O of every chemistry class. But a small fraction of water molecules contain a heavier form of hydrogen called deuterium, hydrogen with an extra neutron in its nucleus. Water made with deuterium is called heavy water, and it behaves slightly differently from ordinary water in ways that scientists can measure with extraordinary precision. The ratio of deuterium to ordinary hydrogen in a sample of water, what scientists call the D/H ratio, is like a fingerprint. Different sources of water in the solar system have different D/H ratios, reflecting the conditions in which they formed. Earth's oceans have a specific D/H ratio. And when scientists measured the D/H ratio of comets, it didn't match. The comets measured, including the famous Halley's Comet and several others studied by spacecraft, had D/H ratios roughly twice that of Earth's oceans. If Earth's water came from comets, the water in our oceans should carry that signature. It doesn't. This was a significant problem for the comet hypothesis. Not a fatal one, there are many different families of comets, and the ones studied might not be representative. And in 2011, the Herschel Space Observatory measured the D/H ratio of a comet called Hartley 2, a member of a different family of comets called Jupiter family comets, and found a ratio much closer to Earth's oceans. The debate is not settled. But the evidence increasingly pointed toward a different primary source. Asteroids. Chapter 5, The Asteroids. Asteroids have a complicated reputation. In popular imagination, they are the destroyers, the rocks from space that ended the age of dinosaurs, that threaten cities in disaster movies, that represent the random, indifferent violence of the universe. But in the deeper story of Earth's history, asteroids played a very different role. They may have been the delivery vehicles for the water that made life possible. A particular class of asteroids, called carbonaceous chondrites, contain significant quantities of water, locked into hydrated minerals within the rock. These asteroids formed in the outer part of the asteroid belt, where temperatures were cool enough for water ice to be incorporated into their structure during the early solar system. When scientists measured the D/H ratio of water extracted from carbonaceous chondrites, it matched. The isotopic signature of the water locked in these ancient rocks was consistent with the isotopic signature of Earth's oceans. This was a significant result. It suggested that the primary delivery mechanism for Earth's water was not dramatic, luminous comets streaking across the sky, but something quieter, more patient, more anonymous. Rocky asteroids, slowly deflected from the outer belt by the gravitational influence of Jupiter, drifting inward over millions of years, striking the early Earth again and again, each impact delivering a small quantity of water locked in hydrated minerals. Not a dramatic delivery. Not a single event. A slow, steady, patient accumulation. Drop by drop. Impact by impact. Millions of years by millions of years. Until there was an ocean. Chapter 6, The Role of Jupiter. There is a planet that may have made Earth's oceans possible. It never gets credit for this. It is not in the story we usually tell about water and life and the unlikely circumstances of our planet. But the evidence suggests that without it, the asteroid belt would never have delivered its cargo of water to the inner solar system. That planet is Jupiter. Jupiter is the largest planet in the solar system, more than twice as massive as all other planets combined. Its gravitational influence reaches across enormous distances, shaping the orbits of countless smaller bodies in ways that have profoundly affected the history of the inner solar system. The asteroid belt, the region between Mars and Jupiter, exists partly because Jupiter's gravity prevented the material there from ever coalescing into a full-sized planet. The gravitational resonances created by Jupiter's orbit stirred the asteroid belt, preventing stable accumulation. But those same resonances also deflected asteroids, particularly the water-rich carbonaceous chondrites of the outer belt, into orbits that crossed the inner solar system. Jupiter, in essence, loaded the catapult. The slow, patient gravitational influence of the largest planet in the solar system redirected water-bearing rocks toward the warm inner worlds, toward Venus, toward Earth, toward Mars. Earth was in the right place. The right size. The right distance from the sun to hold on to what arrived. And so the water stayed. Chapter 7, The Volcanic Contribution. But asteroids were not the only source. There is another possibility, less dramatic, more intimate, built into the structure of the planet itself. Volcanic outgassing. When rock melts, as it does in the mantle beneath the Earth's crust, the gases dissolved within it are released. Water vapor is among the most abundant of these volcanic gases. As the early Earth cooled from its initial molten state, and as volcanic activity continued to reshape its surface, enormous quantities of water vapor were released into the atmosphere. Water that had been trapped within the rock of the early Earth since its formation. Water locked into minerals, incorporated during the accretion of the planet itself from the dust and gas of the protoplanetary disk. As it cooled, it came out. The precise contribution of volcanic outgassing to Earth's total water budget is still debated. Some models suggest it was minor compared to the asteroid contribution. Others suggest it may have been substantial. What seems increasingly clear is that Earth's water did not have a single source. It came from multiple directions. Multiple processes. Multiple billions of years of slow accumulation and cycling and transformation. The asteroids brought some. The volcanic interior released more. And possibly, in amounts that are harder to measure, comets contributed their share as well. Earth's oceans are a mosaic. A collection assembled over deep time from sources spread across the solar system. Chapter 8, The Hadean Ocean. At some point, scientists debate exactly when, but current evidence suggests as early as 4.4 billion years ago, the surface of the Earth cooled enough for liquid water to persist. The steam that had filled the early atmosphere began to condense. The first rain fell. Not a gentle rain. Not the soft, steady rain of a temperate climate. A rain of extraordinary intensity, warm, acidic, falling in quantities that have no parallel in the modern world. For millions of years, it rained. The low-lying areas of the cooling crust filled. The first ocean formed. We call the earliest period of Earth's history the Hadean, from Hades, the Greek underworld, because it was imagined to be a hellish, inhospitable place. And in some ways, it was. The atmosphere was still thick with carbon dioxide and methane and other gases incompatible with life as we know it. The sun was younger and fainter, perhaps 30% less luminous than it is today, meaning that without the greenhouse effect of that thick early atmosphere, Earth's surface would have been below freezing. The bombardment from space had not entirely ceased. Large impacts still struck the surface occasionally, generating enormous amounts of heat, perhaps temporarily vaporizing portions of the ocean. And yet, something extraordinary may have been happening. The oldest minerals on Earth, tiny crystals of zircon found in ancient rocks in Western Australia, date to 4.4 billion years ago. And the chemistry of these zircons suggests that at the time they formed, liquid water was present at the surface. 4.4 billion years ago. Within 200 million years of the planet's formation. The ocean had already arrived. Chapter 9, Why Earth Kept Its Water. Mars also had water. This is not speculation. It is written in the landscape, in the ancient, dry river valleys that cut across the Martian surface, in the mineral deposits that only form in the presence of liquid water, in the traces of ancient shorelines that some researchers believe they can see in the topography of the northern lowlands. Mars had liquid water on its surface for hundreds of millions of years. And then it lost it. The water retreated, underground, to the polar ice caps, to mineral deposits locked in the regolith. The liquid oceans and rivers and lakes that once existed on the Martian surface are gone, replaced by the cold, dry, rust-colored desert we see today. Why did Earth keep its water when Mars did not? The answer comes down to several factors, working together over billions of years. Size. Earth is significantly larger than Mars, about 10 times more massive. That greater mass means stronger gravity, which makes it harder for gases and water vapor to escape into space. Mars, with its weaker gravity, lost its atmosphere, and with it, eventually, most of its surface water, more easily. The magnetic field. Earth has a powerful global magnetic field, generated by the movement of liquid iron in its outer core. This field deflects the solar wind, the stream of charged particles flowing outward from the sun, protecting the atmosphere from being gradually stripped away. Mars lost its magnetic field early in its history. Without that protection, the solar wind gradually eroded its atmosphere over billions of years. And without an atmosphere to maintain pressure, liquid water on the surface became impossible. Plate tectonics. Earth's crust is divided into moving plates, cycling material between the surface and the deep interior in a continuous process that regulates atmospheric chemistry, temperature, and the carbon cycle. This cycling, the carbonate-silicate cycle, acts as a thermostat, keeping Earth's climate within the range where liquid water can persist even as the sun has gradually brightened over geological time. Mars, after its early active period, became geologically quiet. The thermostat stopped working. The climate evolved beyond the range where liquid water could survive. Earth kept moving. Earth kept cycling. Earth kept its water. Chapter 10, The Water Cycle, 4 billion years old. The water on Earth has never stopped moving. From the moment the first ocean formed, 4.5 billion years ago, through every ice age and warm period, every continent rearrangement, every mass extinction and evolutionary explosion, the water cycle has continued. Without interruption. Without end. Water evaporates from the ocean surface, driven by the energy of the sun. It rises into the atmosphere as vapor, invisible, carried by winds across continents and oceans. It cools, condenses, falls as rain and snow. It flows back to the ocean through rivers and groundwater. It enters the bodies of living things, becomes part of their chemistry for a time, and is released again. The same molecules. Moving endlessly. The water that fell as rain on the Jurassic forests. The water that flowed through the rivers of ancient continents whose names we have forgotten. The water that surrounded the first living cells as they assembled themselves in the warm chemistry of an early ocean. It is all still here. Still moving. Still cycling. The water in the glass by your bed tonight has been rain over ancient mountains. It has been ice in glaciers that no longer exist. It has moved through the bodies of creatures that lived and died hundreds of millions of years before the first human being was born. It is incomprehensibly old. And entirely ordinary. And that, perhaps, is the most extraordinary thing about it. Chapter 11, Water and the Origin of Life. Water did not just arrive on Earth and sit quietly in the oceans, waiting. It became the medium in which life assembled itself. Water is, in chemical terms, an extraordinary solvent. It dissolves more substances than almost any other liquid, creating the complex chemical soups from which the molecules of life, amino acids, nucleotides, lipids, could form and interact. It is liquid across a wide temperature range, from 0 to 100 degrees Celsius at normal atmospheric pressure, meaning that on a planet like Earth, it can remain liquid in enormous quantities for billions of years. It is less dense as a solid than as a liquid, which is why ice floats. This unusual property means that when lakes and oceans freeze, they freeze from the top down, preserving liquid water beneath the ice where life can continue to exist through the coldest periods. It participates directly in the chemical reactions of life, not just as a medium, but as a reactant. Photosynthesis splits water molecules. Cellular respiration produces water as a byproduct. The most fundamental processes of living chemistry are written in the language of water. Life, as we know it, is not just surrounded by water. It is made of it. Approximately 60% of the human body is water. The water in your cells is performing chemistry right now, as you breathe, as your heart beats, as your neurons fire in the gentle, quieting patterns of a mind moving toward sleep. You are, in a very real sense, animated water. Water that arrived on this planet 4.5 billion years ago, from asteroids drifting inward from the outer solar system, from the volcanic depths of a cooling world. Water that has been cycling for billions of years. Water that, for a brief and extraordinary moment in geological time, is doing something that water has very rarely done anywhere in the known universe. It is aware of itself. Chapter 12, Other Worlds, Other Oceans. Earth is not the only world with water. This is one of the most significant discoveries of recent decades in planetary science, and it has transformed how we think about the possibility of life beyond our planet. Europa, one of Jupiter's moons, has a global ocean of liquid water beneath its icy surface. The ocean is kept liquid by the heat generated by the gravitational flexing of the moon as it orbits Jupiter. It may contain more liquid water than all of Earth's oceans combined. Enceladus, a moon of Saturn, vents plumes of water vapor and ice crystals from cracks near its south pole. Spacecraft have flown through these plumes and detected organic molecules, hydrogen, and the chemical signatures of hydrothermal activity. Beneath its ice, a warm, chemically active ocean. Ganymede, Jupiter's largest moon, likely has a subsurface ocean larger than Earth's oceans, buried beneath layers of ice. Even Titan, Saturn's largest moon, has a liquid on its surface. Not water, but methane and ethane, forming lakes and rivers and rain in a cold, orange-skied world where the chemistry of life might work in ways completely unlike anything we know. Water, or something functionally similar, turns out to be abundant in the solar system. Not rare. Not special to Earth. Present wherever the conditions allow. Which raises a question that has no answer yet. If water is common, and if water is the medium in which life assembles itself, are we alone? Chapter 13, The Unanswered Question. We do not know where exactly Earth's water came from. This is important to say clearly and without apology. We have models. We have evidence. We have isotopic measurements and computer simulations and the testimony of ancient minerals and the chemistry of meteorites. We have a story that is plausible and internally consistent and supported by the best science we can bring to bear. But the origin of Earth's water is still, genuinely, an open question. The relative contributions of asteroids and comets and volcanic outgassing, the timing of the delivery, the precise mechanisms, the role of Jupiter and the late heavy bombardment, these are things scientists are actively debating right now. New missions are gathering new evidence. New measurements are being made. The models are being refined, year by year, with data from spacecraft that have visited comets and asteroids and the moons of the outer planets. The answer is getting clearer. But it is not yet clear. And there is something genuinely wonderful about that. In a world where it sometimes feels as if everything has been explained, as if the great mysteries have all been solved, as if the era of discovery is behind us. The water in your glass is still a mystery. Not entirely. Not completely. But enough. Enough to remind us that the universe is larger than our current understanding of it. Enough to remind us that the most ordinary things, a drop of water, a handful of ancient rock, the blue shimmer of the ocean seen from space, contain questions we have not yet learned to fully ask. Chapter 14, The Ocean Tonight. Somewhere on the surface of this planet, right now, the ocean is moving. In the North Pacific, deep swells generated by a storm system are crossing 3,000 kilometers of open water, carrying the energy of that distant storm forward in long, low waves that will eventually break on some distant shore. In the South Atlantic, warm surface water is evaporating in the tropical heat, rising, cooling, forming clouds that will eventually become rain over continents thousands of kilometers away. In the deep trenches of the Western Pacific, the cold, dense water that sank near the poles hundreds of years ago, carrying oxygen dissolved from the surface, is flowing slowly along the seafloor, part of the great circulation system that carries heat and nutrients around the globe in a cycle that takes roughly 1,000 years to complete. The ocean does not rest. It is always moving. Always cycling. Always doing the work it has been doing since the first water arrived on this planet, 4.5 billion years ago. Patient. Ancient. Indifferent to the hours. Chapter 15, The Geometry of Water. Before we go further into the story of water, before we follow it through ice ages and oceans and the bodies of creatures that lived and died before we existed, let us stay, for a moment, with the molecule itself. With the thing that water actually is. 2 hydrogen atoms. 1 oxygen atom. H2O. It sounds simple. It looks simple, drawn on a blackboard or printed in a textbook, a central oxygen with 2 hydrogens attached, like a small, lopsided letter V. But the simplicity is deceptive. The geometry of that molecule, the precise angle at which the 2 hydrogens are attached to the oxygen, 104.5 degrees, is responsible for almost everything that makes water extraordinary. Because of that angle, water is what chemists call a polar molecule. The oxygen end carries a slight negative charge. The hydrogen ends carry slight positive charges. The molecule is, in a very small but measurable way, like a tiny magnet, with poles, with attraction, with the ability to interact with other molecules in ways that a symmetrical molecule could not. This polarity is why water dissolves so many things. The charged ends of the water molecule attract the charged components of other substances, pulling them apart, surrounding them, carrying them in solution. Salt dissolves in water because the sodium and chloride ions are attracted to the charged poles of the water molecule. Sugar dissolves because its molecular structure contains charged regions that water molecules surround and carry away. Life depends on this. The chemistry of living cells happens in water solution. Ions move through membranes dissolved in water. Enzymes work in water. The genetic information encoded in DNA is read and copied by molecular machines that work in water. Take the water away, and the chemistry of life stops. Not slows. Stops. And all of this extraordinary chemical generosity, comes from an angle. 104.5 degrees. The geometry of a molecule so small that a single drop of water contains more of them than there are stars in the observable universe. Consider that for a moment. More water molecules in a single drop than stars in everything we can see. Each one of them bent at that precise, life-enabling angle. Each one of them participating, right now, in the chemistry that keeps you alive. Chapter 16, Water as Ice. We have spoken of water as a liquid. As an ocean. As rain and rivers and the chemistry of living cells. But water spends a significant part of its history as something else. As ice. And ice is, in its quiet way, one of the most remarkable substances on Earth. Most substances are denser as solids than as liquids. When they freeze, their molecules pack together more tightly, and the solid sinks in its own liquid. Water does not do this. When water freezes, its molecules arrange themselves into a crystalline lattice, a regular, geometric structure held together by hydrogen bonds, and this structure is actually less dense than liquid water. Ice floats. This seems obvious. We see it every day, ice cubes in a glass, icebergs floating in the ocean, a frozen puddle with air trapped beneath. But the implications of this simple fact are profound. When a lake or a pond begins to freeze in winter, the ice forms at the surface. It floats there, insulating the water below. The liquid water beneath the ice stays cold but liquid, above freezing, protected from the air by that floating layer of ice. And beneath the ice, life continues. Fish. Microorganisms. The chemistry of an ecosystem, continuing through the winter, protected by the extraordinary accident that water is less dense as a solid than as a liquid. If ice sank, the history of life on Earth would have been radically different. Ponds and lakes would freeze solid in winter, from the bottom up. Aquatic life would have no refuge from the cold. The seasonal rhythms of aquatic ecosystems, which have shaped the evolution of countless species, would not exist. Perhaps life would have found another way. Life generally does. But the world would have been different. Different because of an angle. Because water molecules, when they freeze, prefer a geometry that happens to be less efficient, less densely packed, than their liquid arrangement. Because ice floats. Chapter 17, The Ice Ages. The story of water on Earth is, in part, the story of ice. Not the gentle ice of a frozen pond. Not the picturesque ice of a mountain glacier. The ice of ice ages, the periods, recurring throughout Earth's history, when enormous sheets of ice spread from the poles across vast regions of the continents, reshaping landscapes, altering sea levels, transforming the climate of the entire planet. The most recent ice age, or more precisely, the most recent glacial maximum within the current ice age, which technically continues today, peaked approximately 20,000 years ago. At that time, ice sheets up to 3 kilometers thick covered most of North America, most of Northern Europe, and large parts of Asia. The sea level was roughly 120 meters lower than it is today. Coastlines that are now underwater were dry land. The English Channel was a river valley. The islands of Southeast Asia were connected to the Asian mainland in a continuous landmass. And the climate was so different from today that if you were transported there without preparation, to the edge of the ice sheet, in what is now southern England or northern Ohio, you would find a landscape that looked more like the modern Arctic tundra than anything familiar. Cold. Vast. Windswept. Covered in grasses and sedges and the occasional stunted tree. Roamed by woolly mammoths and woolly rhinoceroses and cave lions and giant ground sloths. A world that is gone. But the water that formed those ice sheets is not gone. It is still here, cycling. Some of it is locked in the ice that remains, in Antarctica and Greenland and the mountain glaciers that are, in our current warming climate, beginning to retreat. Some of it has been rain, many times over, since the ice melted. Some of it is in the ocean, in the groundwater, in the bodies of living things. The water that was ice above New York City 20,000 years ago might be in the glass by your bed tonight. Cycling. Always cycling. Chapter 18, The Snowball Earth. There is a period in Earth's history, or possibly several periods, more extreme than any ice age of the recent past. A time, or times, when the glaciation was so severe that ice may have covered the entire surface of the planet. Down to the equator. Down to the tropics. Everywhere. The world, frozen solid. Scientists call it Snowball Earth. The evidence for it is geological, ancient glacial deposits found in rocks that, at the time they were formed, were near the equator. Distinctive chemical signatures in ancient rock formations that suggest a sudden, catastrophic change in atmospheric chemistry. The pattern of certain mineral deposits that are consistent with a global freeze and a rapid, dramatic thaw. The most widely accepted model suggests that snowball Earth events occurred several times during the Proterozoic era, roughly between 700 million and 600 million years ago. Before complex animal life existed. In a world dominated by bacteria and simple algae. The mechanism, as scientists understand it, involves a feedback loop. Ice reflects sunlight, more than liquid ocean or bare rock. As ice spreads, it reflects more solar energy back into space, cooling the planet further, causing more ice to form. A runaway cooling. Once started, this process could, under the right conditions, reach the equator, a global freeze from which, it would seem, there was no escape. And yet, the Earth escaped. Because even during a snowball Earth event, the volcanoes continued. Beneath the ice, the Earth's interior was as hot as ever. Volcanic eruptions continued, releasing carbon dioxide into the atmosphere. But with the surface frozen and photosynthesis greatly reduced, there was nothing to remove that CO2 from the atmosphere. It accumulated. Over millions of years. Slowly. Patiently. Until the concentration was hundreds of times higher than today, a super greenhouse effect, and the ice began to melt. Not slowly. Once the ice began to retreat, the same feedback loop that had frozen the planet now ran in reverse. Less ice meant less reflected sunlight meant more warming meant less ice. A runaway thaw. The snowball Earth episodes likely ended with a period of extraordinary warmth, perhaps the most extreme climatic shifts the planet has ever experienced, swinging from a global freeze to temperatures far above anything that exists today. And through it all, the water persisted. Locked in ice. Cycling through the thin liquid layer that may have persisted beneath the ice at the equator. Released in the explosive thaw. Still here. Still cycling. Still the medium in which life, somehow, endured. Chapter 19, The Rivers. We have followed water into the deep ocean and up into the ice. Now let us follow it somewhere more familiar. Down from the mountains. Into the rivers. A river begins as rain. Or as snow melt. Or as the slow seepage of groundwater from a hillside, gathering in a trickle too small to have a name, joining other trickles, becoming a stream, joining other streams, becoming something larger. Something with momentum. With direction. With the particular, patient, inexorable logic of water moving toward the lowest available point. Rivers are among the most powerful forces of landscape change on Earth. They cut canyons. They build deltas. They carry sediment from mountains to the sea. They reshape coastlines. They deposit the rich, fine-grained soils of floodplains that have supported agriculture for 10,000 years. The Nile built Egypt. Not the pharaohs, the Nile. The annual flooding of the Nile deposited the rich dark sediment that made the desert bloom, that fed a civilization for 3,000 years, that shaped the course of human history. The Amazon carries more water than the next 7 largest rivers on Earth combined. Its discharge into the Atlantic is so enormous that fresh water can be detected in the ocean hundreds of kilometers from the river mouth. The Mississippi drains 31 states and 2 Canadian provinces. Every drop of rain that falls on that enormous basin, on the corn fields of Iowa, on the forests of Minnesota, on the mountains of Montana, eventually finds its way to the Gulf of Mexico. Rivers are the arteries of continents. They carry water, and in water, nutrients, sediment, the chemical material of the landscape, from the high places to the low places, from the interior to the sea. They have been doing this for as long as the continents have existed. On Mars, there were rivers once. We can see the dry beds of them, broad, branching channels carved by flowing water into the ancient Martian rock, now dry and cold and still under a thin, cold sky. They ran for hundreds of millions of years. They stopped. On Earth, the rivers continue. They will continue, in some form, as long as the sun shines and the water cycle turns. Chapter 20, Water Underground. Not all of Earth's water is visible. Far from it. Beneath the surface, beneath the soil, beneath the bedrock, beneath the layers of sediment and stone, there is water. Groundwater. Filling the tiny spaces between grains of rock. Moving, almost imperceptibly slowly, through porous rock formations called aquifers. Pooling in underground reservoirs that took thousands or millions of years to fill. The total volume of groundwater on Earth is enormous, far more than all the water in all the world's rivers and lakes combined. It is the largest reservoir of fresh liquid water on the planet. And it is ancient. Some groundwater, in deep aquifers far from the surface, has been underground for hundreds of thousands of years. In certain formations in the Sahara, water drawn from wells dates to the last ice age, when the climate of North Africa was wetter, when rain fell on the land that is now desert, soaking into the rock and slowly, patiently moving through it. Fossil water. Water from a world that no longer exists. We are pumping it out today, for agriculture, for cities, for the needs of billions of people, faster than it can be replenished. Some of it will not be replaced for thousands of years, if ever. There is something worth sitting with in that thought. The water we use today may have last seen the sky when human beings were still living in small, scattered groups of hunters and gatherers. When the animals of the Ice Age still roamed the earth. When the world was cold and vast and only beginning to understand what it was becoming. Chapter 21, Water and Civilization. Water made civilization possible. not as a metaphor. Literally. Every great civilization in human history has been built on water. The Tigris and Euphrates rivers gave rise to Mesopotamia, the first cities, the first writing, the first legal codes, the first recorded history. Ur and Babylon and Nineveh, built on the banks of rivers that brought life to an otherwise arid landscape. The Nile gave rise to Egypt. The Indus to the Harappan civilization. The Yellow River to ancient China. The rivers of Central America to the Maya. The pattern repeats, across every continent, across every era of human history. People settled where water was. They built where water was reliable. The water that flows through the modern pipes of Rome follows, in part, routes that were laid out by Roman engineers 2 millennia ago, moving downhill at a carefully calculated gradient, driven by nothing more than gravity and the patience of water finding its level. Water does not hurry. It does not need to. It has time. Chapter 22, The Water in You. We said earlier that 60% of the human body is water. Let us stay with that for a moment. Not as a statistic. As a reality. You are, right now, mostly water. Your blood is about 90% water, a fluid remarkably similar, in its salt concentration, to the ancient ocean that your distant ancestors left hundreds of millions of years ago. The ocean, carried inside you. A small, private ocean, pumped in a continuous circuit by a muscle no bigger than your fist. Your muscles are about 75% water. Your brain, the structure that is reading these words, processing them, finding meaning in them, is about 73% water. Your bones, which seem as far from water as it is possible to be, solid and dry and permanent, are 31% water. Even your fat cells, which hold less water than almost anything else in the body, are still about 10% water. You are, in a real and physical sense, a vessel. A vessel that water moves through. You take in approximately 2 to 3 liters of water each day, through drinking and through the water content of food. You release approximately the same amount, in urine and breath and sweat and the invisible water vapor that leaves your body with every exhale. You are not the same water you were a week ago. The molecules that are in your blood right now, carrying oxygen to your cells, will have been replaced, drunk, absorbed, used, and released, in a matter of days. You are a pattern that water moves through. A structure maintained not by the permanence of its material but by the continuity of its form. Like a river. Like a wave. Like everything, in the end, that persists in this world, not by staying the same, but by continuously, gracefully, becoming itself again. Chapter 23, Rain. Let us think about rain. Not the dramatic rain of a thunderstorm. Not the rain of floods and emergencies. The ordinary rain of an ordinary afternoon. The kind that comes slowly, almost apologetically, softening the air before it arrives. The kind that you can smell before you can hear, petrichor, the word for that particular scent, from the Greek petra for stone and ichor for the fluid that flows in the veins of the gods. The smell of rain on dry earth. It comes from a compound called geosmin, produced by bacteria in the soil, bacteria that thrive in wet conditions and release this aromatic molecule when raindrops disturb them. That smell, ancient, familiar, one of the most universally recognized scents across human cultures, is, in essence, the smell of life responding to water. The bacteria, awakening. Celebrating, in their bacterial way, the arrival of what they need. Rain has been falling on Earth for 4 billion years. The same physics. The same chemistry. The same cycle: evaporation, condensation, precipitation, flow. Water vapor rising from the ocean. Cooling as it rises. Forming droplets around tiny particles of dust and pollen and sea salt. Growing heavy enough to fall. It fell on the dinosaurs. It fell on the first forests of the Carboniferous period, on trees that no longer exist, on landscapes that have been transformed beyond recognition by hundreds of millions of years of geology. It fell on the Permian Sea, on the Devonian Reef, on the Cambrian Ocean, where the first complex animals were learning what it meant to have a body. It has been falling for so long that the concept of the first rain, the first condensation, the first drop falling onto the cooling surface of an early Earth, is almost impossible to hold in the mind. And tonight, somewhere on this planet, it is falling. On a forest, on a rooftop, on an ocean that is already full of it. Still falling. Still cycling. Still doing what water has always done, in this world and possibly in others. Chapter 24, Water on Other Worlds. We have spoken of Europa and Enceladus, the moons of the outer solar system that hide liquid water beneath their icy surfaces. Let us go there, briefly. To Europa. Europa is slightly smaller than our moon, a world of ice and rock, orbiting Jupiter at a distance that brings it under the enormous gravitational influence of the solar system's largest planet. That gravitational influence is not gentle. As Europa orbits, Jupiter's gravity squeezes and stretches it, flexing the rock and ice of the moon's interior, generating heat through friction. Enough heat to maintain a liquid ocean beneath the ice. An ocean that may be 100 kilometers deep. An ocean that has been liquid, potentially, for billions of years. When the Voyager spacecraft flew past Europa in 1979, the images showed a surface covered in cracks and ridges, a pattern that looked, to the scientists studying it, remarkably like the sea ice of the Arctic Ocean on Earth. Ice fractured by the movement of liquid water beneath it. Ice that had frozen and refrozen, shifted and cracked and healed again over geological time. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, returned more detailed images and measurements that confirmed the presence of a subsurface ocean. The magnetic field measurements were particularly compelling. The pattern of fluctuations in Europa's magnetic field was consistent with a conducting fluid beneath the surface. A salty ocean, generating electrical currents as Europa moved through Jupiter's magnetic field. In that ocean, beneath kilometers of ice, in the complete darkness of a world far from the sun, what happens? We do not know. The ocean is real. The darkness is real. The heat from Jupiter's gravitational squeezing is real enough, possibly, to support hydrothermal activity on the seafloor, similar to what we find in Earth's deep ocean. And where there is liquid water, and heat, and chemistry, perhaps there is life. We have not found it. We have not looked, not really, not with instruments capable of detecting it. But the possibility is there. In the dark water of a frozen moon, 60 kilometers below a surface of cracked ice, orbiting a planet that shows as a giant bright star in a sky that has never seen the sun clearly, something might be swimming. Chapter 25, The Sound of Water. Water has a voice. Not a metaphorical voice. An actual acoustic presence, the sounds it makes as it moves through the world, as it falls, as it flows, as it meets resistance and finds its way around it. The sound of rain on leaves. On a roof. On still water, each drop creating a brief circle of ripples and a soft, repeating percussion. The sound of a river, not the roar of rapids, but the quieter sound of moving water over stones. A continuous, irregular music that contains frequencies that human beings find, almost universally, soothing. The sound that sleep machines and meditation apps try to replicate, with varying success. The sound of the ocean, the long, slow breath of waves breaking and withdrawing. A sound with a rhythm that echoes, just slightly, the rhythm of breathing. In. And out. In. And out. There is evidence that these sounds, water sounds, have a measurable effect on the human nervous system. They activate the parasympathetic nervous system, the part of the nervous system that governs rest and recovery. They reduce cortisol. They slow the heart rate. They move the brain toward the slower wave patterns associated with relaxation and the early stages of sleep. We have been hearing water since before we were born. The womb is a water environment, the fetus surrounded by amniotic fluid, hearing the muffled sounds of the body from within that liquid world. The sound of blood flowing. The sound of breath. The sounds of the outside world, filtered and softened by water. Perhaps the soothing quality of water sounds is, in part, a memory. The first environment. The water world inside another water world. Home. Chapter 26, The Deep Aquifers. Beneath the dry lands of the world, beneath deserts and plains and ancient mountain ranges, water waits. In the Nubian sandstone aquifer system, stretching beneath Libya and Egypt and Sudan and Chad, water that fell as rain during the last ice age, when the Sahara was a land of lakes and rivers and green grassland, filtered down through the rock and has been there ever since. Approximately 150,000 cubic kilometers of it. Still. Patient. Cold. Waiting in the darkness of the rock, in spaces too small to see without a microscope, held by capillary forces and the weight of the world above. This water has been underground for tens of thousands of years. It has not seen the sky since the mammoths roamed and the last ice age was fading. In the Great Artesian Basin of Australia, one of the largest groundwater systems in the world, stretching beneath parts of Queensland and New South Wales and South Australia, some of the water is estimated to be 2 million years old. 2 million years. Moving through rock so slowly that a molecule of water might travel a meter in a year. Patient beyond our ability to truly imagine. When it is pumped to the surface, for the cattle stations of the Australian outback, for the towns and communities of arid inland Australia, it often rises with heat. Geothermal energy, absorbed from the rock over those millions of years of slow descent. Ancient water. Warm from its long journey through the earth. Arriving at the surface as if waking from a very long sleep. Chapter 27, The Future of Water. The water on Earth is not going anywhere. Not in any meaningful sense, not over the timescales of human history. The total amount of water on Earth has remained roughly constant for billions of years. It cycles, between ocean and atmosphere and ice and rock and the bodies of living things, but it does not disappear. The molecule is extraordinarily stable. Water can be split, by ultraviolet radiation, by electrolysis, by certain chemical reactions, into hydrogen and oxygen. The hydrogen, being light, can escape Earth's gravity and be lost to space. This process happens, very slowly, at the top of the atmosphere. Over the entire history of Earth, the total loss of water to this mechanism amounts to a small fraction of the total water budget. Not enough to drain the oceans. Not enough to matter, on geological timescales. Earth's water is here to stay. But water in the right place at the right time, that is a different question. Fresh water. Liquid water. Water that is available, clean, at the surface, accessible to the people who need it. That is not guaranteed. We live on a planet with abundant water, but the water is not distributed equally. Not in space. The rainfall and river systems and aquifers of the world are concentrated in some regions and absent from others. Not in time, wet seasons and dry seasons, wet decades and dry decades, the irregular rhythms of a climate system that has never been entirely predictable. And the climate is changing. The patterns of rainfall are shifting. The glaciers that provide summer meltwater to the rivers of Asia and South America, feeding billions of people, are retreating. The aquifers that took thousands of years to fill are being pumped down in decades. The water is still here. The cycle is still running. But the relationship between human civilization and water, the relationship that has sustained every city, every farm, every culture that has ever existed, is under pressure. Water, patient and ancient as it is, does not negotiate. It falls where the physics take it. It flows where the gradient leads. It does not arrive on schedule. It does not ask whether we are ready. Chapter 28, Water as Meditation. In many of the world's contemplative traditions, water is used as a focus for meditation. For the quieting of the mind. In Zen practice, the image of water is used to describe the ideal state of mind, clear, still, reflecting everything without clinging to any of it. A mind like still water shows the sky above it without being the sky. It reflects a passing cloud without becoming the cloud. It holds an image and releases it without effort, without resistance. The Tao Te Ching, the ancient Chinese text attributed to Laozi, returns again and again to water as an image of the highest virtue. Water benefits all things and does not compete. It goes to the low places that others disdain. It is soft, and yet it wears away stone. It does not force, and yet nothing can stop it. The highest good is like water. There is something in the nature of water, its flexibility, its persistence, its ability to find a way through any obstacle not by force but by patience, that the human mind recognizes as wise. Perhaps because water is what we are made of. Perhaps because the patterns of water are the patterns written into our cells, into our chemistry, into the deep logic of life that assembled itself in water 4 billion years ago. Water knows things that we have forgotten. It knows how to move without forcing. How to rest without stopping. How to find the lowest place and be content there. How to be still, and in its stillness, reflect the whole world. Chapter 29, The Last Drop. Every drop of water has a history. Not a metaphorical history. A real one. A history of geological time, of the solar system, of the slow accumulation of molecules on a planet that formed too close to its star to have water of its own. The water that is in you tonight came from somewhere extraordinary. It formed in the cold of the outer solar system, in the icy mantles of asteroids drifting in the ancient disk of material from which the planets were assembling. It traveled inward, over millions of years, deflected by the gravity of Jupiter, crossing the vast distances of the young solar system. It arrived on the young Earth in the slow, patient bombardment of the Hadean era, impact by impact, molecule by molecule. It was rain on a young world that no human eye ever saw. It was part of the first ocean. It has been frozen in glaciers that no longer exist. It has moved through the bodies of creatures that lived and died hundreds of millions of years before the first human being was born. It has been rain over forests of species we have never named. It has been ice in ice ages. It has been carried in rivers to seas that no longer exist. And tonight, it is here. In you. In the glass by your bed. In the quiet air of the room where you are resting. Still cycling. Still moving. Ancient. Patient. Ordinary. Extraordinary. Chapter 30, The Still Water. It is very late now. Outside, the world has quieted. Let your body settle into the stillness. Let your breathing slow. In. And out. Water, moving in and out of you with every breath, vapor leaving with each exhale, water absorbed with each inhale of humid air. You are always, even now, part of the water cycle. Even at rest. Even in sleep. Let the thoughts of the day drift away. Not by force. Not by effort. The way sediment drifts down through still water. Slowly. Without resistance. Settling softly on a quiet floor. Think, for a moment, of still water. A lake at night. No wind. No ripples. The surface so smooth it is a perfect mirror, holding the sky, the stars, the dark shapes of trees at the water's edge. Everything reflected. Nothing disturbed. That stillness is available to you. Not because you must achieve it. Not because you must force it or earn it. But because stillness is what water returns to, when nothing disturbs it. And you are water. Mostly. In your cells, in your blood, in the slow chemistry of a body preparing for sleep. Let the surface of you grow still. Let the reflections settle. Let the small disturbances, the thoughts, the sounds, the traces of the day, pass across the surface and fade. Until there is only the stillness. The dark, quiet, ancient stillness of water at rest. Somewhere, rain is falling on an ocean that does not notice it. Somewhere, deep in the rock of a continent, water moves so slowly that a year is barely a footstep. Somewhere, in the ice of a comet in the outer solar system, water molecules wait in crystalline stillness for a journey that may begin in 1,000,000 years. And here, in the warmth and the quiet, your own water rests. Your cells, their chemistry slowing for the night. Your blood, moving in its ancient circuit. Your breath, in and out, in and out. Like the movement of tides. Like the oldest rhythm on earth. Water knows how to rest. It has been doing it for 4.5 billion years. Let it rest now. Let it carry you through the dark hours. Quietly. Patiently. All the way to morning. Close your eyes. The water inside you knows the way. Sleep.